Hello everyone, I am Hana Alghamdi, a PhD student at Trinity College Dublin, and I will be presenting batch-based color transfer using SIFT flow paper. We will start with an introduction and motivation, and then we will present the proposed algorithm, and then present the results, and lastly, the conclusion and future work. Color variation between photographs often happen due to illumination changes, or using different cameras, or using different in-camera settings, or due to tonal adjustment by the users. And color transfer methods have been developed to transform a source color image into specific target color palettes to match color statistics and eliminate this variation between different photographs. And there is many application in image processing, ranging from generating color consistent image stitching to color enhancements and style manipulation for artistic design. When computing the transfer function considering color information only, that doesn't take into account the fact that coherent color should be transferred to neighboring pixels, which can create results with blocky artifacts, emphasizing JPEG compression blocks or increased noise. To tackle this problem, Alghamdi and others proposed the batch-based color transfer, denoted as BCTOT, that encodes overlapping neighborhood of pixels taking into account both color and pixel positions. This algorithm not only shows improvement over the state-of-the-art method, but also shows a limitation by creating shadow artifacts when there are large changes between target and source images, like these examples shown in the slide. And the mapping they are using is optimal transport. And optimal transport, by definition, doesn't take into account any available correspondences when computing the optimal solution. So in this paper, we propose a color transfer methods that match color of images with overlap scenes that may exhibit large motion changes between the images. We do this by improving the BCTOT method by estimating motion flow using the SIFT flow method. SIFT flow method estimate dense spatial correspondences by robustly aligning complex scenes pairs containing significant spatial differences. And we incorporate these estimated spatial correspondences in the encoded overlapping neighborhood of pixels. And this new formulation makes optimal transport implicitly takes into account correspondences when computing the optimal solution. And our second contribution is to introduce smoothing as part of the iterative algorithm for solving the optimal transport, namely the IDT algorithm and the Sliced Wasserstein algorithm. The first step of our algorithm is combining the color and spatial information. So let us assume P is the 2D grid coordinate position of the pixels in the target image, and WB is the flow vector estimated using the SIFT flow method. And the corresponding position of these pixels in the source image can be computed by adding B and BW. Then we concatenate, after computing these new positions, we concatenate the color and the new position to into a vector Y in 5D space. So 5D comes from the 3D RGB colors and the position 2D. The second step is data normalization. We normalize all the color and pixel positions coordinate to lie between 0 and 255 to create a hypercube in the new space 5D, and then we stretch that space in the direction of the spatial coordinate by a factor 10. The stretching gives the pixel position a big influence on the estimated mapping. It kind of forcing the algorithm to match colors with the same pixel positions. The third step is creating batch vectors. We, in a similar way to BCT, encode overlapping neighborhoods of pixels to preserve local topology, using a sliding window operation of size 5 by 5 to extract these overlapping batches. And from each individual batch, we create a high-dimensional vector in 125-dimensional space. This comes from concatenating every pixels in the batch, where each pixel is 5D dimension space. Step 4 is the iterative projection transfer using IDT or Sliced Wasserstein. We iteratively project point values originally in the high-dimensional space to 1D subspace and find the 1D solution of the optimal transport, and then propagate the solution back to the original space. This operation is repeated with different directions in 1D space until convergence. At each iteration of this algorithm, we proposed to smooth the estimated optimal transport solution by feeding the optimal transport estimated correspondences to the non-parametric Nadaria-Watson estimator to compute a smooth optimal transport. Step 5 is merging recolored candidates. Due to overlap batches, we now have several recolored candidates for every pixels in the source image. So we compute the average color value from these candidates and use it in conjunction with the original position to create the output recolored image. In this slide, we provide our results. We provide quantitative evaluation for our approach, noted here as OT in W, and we compare it to different state-of-the-art color transfer methods. In these evaluations, we use image pairs with similar contents from an existing dataset. These datasets include registered pairs of images, source and target, taken with different cameras and different in-camera settings and different illuminations and recoloring styles. To assess the recoloring results, we use four metrics, which is peak signal to noise ratio, PSNR, and structural similarity index, SSIM, and the color image difference, CID, and the feature similarity index, FSIMC. These metrics are often used when considering source and target images of the same content. We show here the box blocks carrying a lot of statistical details, but please do refer to our paper for tables of details quantitative results. The PSNR evaluation on the left figure and FSIMC on the right figure. By examining these box plots, we see that the form method BMLS, L2, BCTOT, and our algorithm OT in W are greatly overlapped with each other. The median, shown as black horizontal lines, and the mean, shown as red dots, are the highest among all algorithms and are very close in value, and the whiskers length almost similar, indicating similar data variation and consistency. Here we have SSIM on the right and CID evaluation on the left. By examining the SSIM box plot, we can see that our algorithm OT in W performs similarly to BMLS and L2 scoring the highest value and BCTOT scoring the lowest value among the three. In CID evaluation on the left, our method performs similarly to BMLS and L2 and BCTOT. In conclusion, the quantitative metrics show that our algorithm with Nadaria-Watson smoothing performs similarly with top methods BMLS, L2, and BCTOT, and outperforms the rest of the state-of-the-art algorithms. Here, we provide qualitative evaluation. For clarity, the results are presented in image mosaics created by switching between the target image and the source or the result image column-wise. For example, if you look at the image at the top right, one column comes from the source and one column comes from the target. And because there is a difference between the source and the target colors, we can see columns differences. And if the color transfer is accurate, the resulting mosaic for each method should look like a single image. Otherwise, you will see column differences. As can be noted, our algorithm in the last column in the results, OT in W, is successful in removing the column differences. Here we have more qualitative evaluation. We pick the top method that score highest quantitative values in terms of metrics measured and compare their result with our result visually. Although BMLS and PCT OT provide equivalent result to our methods in terms of metric measures, BMLS introduce visual artifacts if the input images are not registered correctly. And we can see this in the example Ilm in the second row with the car, while our algorithm is robust to registration error. In addition, due to the Nadarya-Watson smoothing steps, our algorithm allows us to create a smoother color transfer results and can elevate the JPEG compression artifacts and noise. And we can see in the our examples, it's a smoother. And another observation specific to a BCT-OT algorithm, we said before, it can create shadow artifacts when there are large changes between the target and the source images, as in the example building in the third row. While our method, OT in W, can correctly transfer colors between images that contain significant spatial differences and elevate these shadow artifacts, as can be seen in the building example and also in Ilm with the car, as the car between the source and the target, the cars are completely different. And also in the Mart example, the last row, there is a change between the source and the target image. Several contributions made in this paper. First, correspondences information as well as color content of pixels are both encoded in high-dimensional feature vector, making optimal transport taking into account implicitly the correspondences information when computing the solution. And we have introduced smoothing as part of the iterative algorithm for solving the optimal transport, namely IDT and Sliced Wasserstein Distance. Our algorithm allows denoising, artifact removal, as well as a smooth color transfer between images that may contain large motion changes. As for the future work for this paper, it was a method with Nadarya-Watson that map one n-dimensional distribution to another. We implemented this method and submitted the paper to Multimedia Signal Processing Conference and has been accepted for presentation in September. And these are the references. Thank you. Any questions?